Welcome, welcome, welcome. What a nice time to be alive, to be a member of life, to never witness history, to never read history, but to be part of it. So come and witness history with me. I'm going to show you how do you kill Euclidean geometry. So first thing, we need weapons because as soldiers, before soldiers go to wars, they make sure that they have enough weapons and working weapons. So that's what we are going to do. So before I start with everything, I would like to give shout out to Mr. Henry Walton. I don't know if he was the lecturer or he is the lecturer at that time. I went through his video on Euclidean geometry, and that's how I got the idea behind Euclidean geometry. So don't forget to hit the subscribe button and keep on sharing these videos that I post. So the first area of focus is parallel lines. So I know someone out there might say, what is this guy doing telling us about parallel lines? But there's a vital connection between parallel lines and Euclidean geometry. So let's see what we know about parallel lines. We know simple things, but don't don't focus more on what the parallel lines say. Focus on the conjecture that comes out of the parallel lines. How can you use parallel lines to combat problems in Euclidean geometry? So let's start. Let's get to it. Basic things. We know we have f. This is fun, or some people call it fuzz. It does not matter. So this is our parallel lines. So grade 11s and grade 12s. I want you to see the idea here. So this is A, B, C, D. Let's say E, F, G, H. No problem. So these are parallel lines. Okay. What we know is this is corresponding angles, and then this is co-interior angles, and then this is alternate angles. So this is what we know about parallel lines. So let's check. If we know that AB is parallel to CD, what we know is A1 equals C2. Okay, that's nice. A1 equals C2. And then what will be the reason? The reason will be corresponding angles. I want you to notify that. No problem. Okay, what can we say about this one of you? What we can say is A, B, C, which we are referring to this angle, plus we can just say D or B, B, C, D equal 180 degrees. So what do we know? We know that if these two lines are parallel and they form U, then we know that the interior angles, when you add them, you must get 180 degrees, or we say they are supplementary. Supplementary. They are supplementary angles. That means they add up to 180 degrees. This is what we know. Okay, so now let's look at the last one. The last one, what we know is we know that F, E, G, which means we are referring to that angle. It's F, E, E with a cap. It means we are referring to that angle, G. So this is the angle we are referring to. Is equal to E, G, H with a cap. We are referring to that angle. So if you can spot these things, I'm going to show you the conjecture behind them and how they are used in Euclidean geometry. So this is corresponding, this is cointerior, and then that's alternate. So let's go and see the conjecture in Euclidean geometry. So this is F, and then that's U, and then that's N. So that's A, B, C, D, 1, 2, 3. This is A, B, C, D. You can just put them randomly, it does not matter. So this is A, B, C, D. So now I'm going to give you values in these things. So let's say this one equal 10 degrees and that's one equal 10 degrees. And we say this one is 120 degrees and that one is 60 degrees. That one is 75 degrees and that one is 75 degrees. So now, let's say this is what you have. You know that, okay, my A3, it's 10 degrees, and then my C1 is 10 degrees. So now, you remember that if two lines are parallel, then the corresponding angles, this one must be equal to that one. That's what we know. So look at the case here. We are being told that A3 equal C1, but we are familiar with this thing, with this shape that is being formed here, the corresponding angles being equal. So now, what will be the conclusion? The conclusion will be AB is parallel to CD. Why are we saying AB is parallel to CD? Simply because corresponding angles are equal. So that's the conjecture in Euclidean geometry. If you don't know that two lines are parallel and you want to prove, find two pairs of corresponding angles. And if you can prove that those two pairs of corresponding angles are equal, then we can conclude by saying that those two lines are indeed parallel. So let's go to the second one. This is 120 and then that's 60 degrees. So what do you say about the lines? Yes, correct. They are parallel. Why are they parallel? So we say AB, which is this line, is parallel to CD, which is this line. So why are we saying this? Why is this true? Simply because co-interior angles are supplementary. Remember, we used supplementary and we said they add up to 180 degrees. If you don't want to use supplementary, you can just say co-interior angles add up to 180 degrees. If the co-interior angles add up to 180 degrees, then those two lines are parallel. So this is parallel and that's parallel. Why are we saying they are parallel? Because here corresponding angles are equal and here co-interior angles add up to 180 degrees. So now let's look at the last one. Looking at the last one, let's compare. Let's look at these and these. So now, if these two lines are parallel, then the alternate angles, which are those angles, they are equal. So now let's look at this one. So they're telling us that's 75 and that's 75. So what do you notice? We are familiar with this thing. From where? From what we learned about parallel lines. So if this is the case, if this is 75 and that's 75, we can say AB is parallel to CD. Why are we saying that? So the reason will be alternating angles are equal. So whenever alternating angles are equal, then those two lines, they must be parallel. So now in Euclidean geometry or in riders, if the question says prove that AB is parallel to CD, how will you prove it? First one, identify alternate or corresponding angles and prove that they are equal, or identify co-interior angles and prove that they add up to 180 degrees, or identify alternate angles and prove that they are equal. So I will show you the application of these things or how to prove parallel lines. So that's the first thing that you need to master. So we know parallel lines. How do you prove parallel lines? You just identify two angles that are corresponding, two angles that are co-interior, two angles that are alternate. And then from there, I will show you what the good teacher known by Henry Walton, I will show you what he did. Okay, so now let's go to the second part. Now you know the parallel lines, you know how to prove it, you know them. So now let's take a look at the second one, which is the triangles. We have different types of triangles. So the first one that I'll focus on, which is the basic, I think in grade 11 and in grade 12, I think you know this one, but I will emphasize it. So now, suppose you have a triangle. This is a basic triangle. So now, if someone comes and say, take 5 million, guess, tell me anything that you know about this triangle. Are you going to lose that 5 million? Never. What you will say is angle A plus angle B plus angle C equal 180 degrees. And then you get your money. So angle A plus angle B plus angle C equal 180 degrees. Why are you saying that? The reason is sum of angles of triangle. What we know is sum of angles of a triangle, they add up to 180 degrees. So this will be one of the most one of the important basic that you need to master, or that you need to know. So now this is number one on triangles, and then number two. So we have this triangle here. This is A, this is B, and this is C. So this one is just a basic one, you know it. This is equilateral triangle. So what do you know about equilateral triangle? All the angles inside, they are equal. So that basically means angle A equal angle B equal angle C. So now, if they are all equal, what is the size of each angle in this thing? So on triangles, so this is sum of angles of a triangle, and then this is equilateral triangle. So we're saying all these angles, they are equal because this is an equilateral triangle. So let's check if this one is x, what will be b? B will be x, and then what will be c? C will be x. So now, using this one, what do you know about that one? If you add all those angles, there must be 180. So that means x plus x equal 180 degrees. What's the reason? Is the sum of angles of triangle. So now x plus x, that's 3x equal 180 degrees. Therefore, x will be 60 degrees. If you divide each side by 3, you will get x is 60 degrees. So in equilateral triangle, what we know is each angle is 60 degrees. So now you basically know these things, so I'm just going through them. So now the third one is this one, and I'm going to put a star on this one because it plays an active role in Euclidean geometry. I'm putting a star. This plays an active, let me put 3 stars. It plays an active role in Euclidean geometry because I'm going to show you what is its application. Remember, like with parallel lines, we deal with the theorem as it is, and then we deal with conjecture. So now this is isosceles triangle. You know everything about isosceles triangle. Those sides which are equal, that basically means the angles which are opposite to those equal sides, they are equal. So if you look at AC, so which angle is opposite to AC? That's B. And then which angle is opposite to AB? That's C. So therefore, we can say angle B equal angle C. And then what will be the reason? So the reason will be angles opposite equal sides. So now let's check. Let's change this thing. Let's say this is A, that's B, and then that's C. Let's say this is 40, this is 40. So now you see it's the same thing, the same idea. If the sides are equal, we know that the base angles, they must be equal. So now what if the base angles are equal? What do you say about the sides? You say that AB equal AC. And then what will be the reason? You look at the reason, it's angles opposite equal sides. So this one will be equal sides opposite angles. So it's just a reverse of that thing. Or you can just say the converse of isosceles triangle. I can accept this one. This is just the converse of isosceles triangle. So this is the idea behind this thing. Let me show you the last part on how they use Euclidean geometry to measure you. So to prove sides in riders, it means in Segel, in grade 11 Euclidean geometry and grade 12 Euclidean geometry. So if a question say, prove that AB is equals to BC, what must come to your mind? Or if the question say, prove that triangle ABC is isosceles, what must come to your mind? What must come to your mind is proof base angles are equal. This is how you prove sides in Euclidean geometry. You prove that the base angles are equal. So now, I'm going to show you, I'm putting stars here. So I'm going to show you how I am going to use the same idea to prove difficult questions, difficult riders, using the same idea, basic idea. So if they say prove that the two sides are equal, check if you can find the base angles and prove that those base angles are equal. If you can prove that they are equal, then you got the marks. So now the third one, okay, the last triangle. The last triangle it's the exterior. So let's look at this triangle. As I said, grade 12 and grade 11, this is just basic knowledge to you. So this is our exterior, the triangle with exterior angle. So now, what do we know about this one? Okay, what we know is the one that is outside. Which one is outside here? It's C1. Is equal to the 2 that is inside, but not the one that is next door. So if you look at C1, what is next door to C1? It's C2. So now I am saying the one that is outside is C1 is equal to the 2 that are inside, but not the one that is next door. So that basically means the ones that are inside is B, it's A, and C2. But my statement says not the one that is next door. So not this one. So that means C1 equal A, okay, plus B. So C1 equal A plus B. What is the reason? It's exterior angle of triangle. And then you are done. So this is also important and vital. Let me put stars here. Because those ones with stars, we are going to use them to prove some of the theorems. But I'm not going to prove theorems today. I'm just showing you basic concepts or basic theorems that you need to master when you take a course in Euclidean geometry. So now, the another part, we know straight line, and then we have straight line. So I'm going to be fast on these ones because I think most of you will be bored now. So this is a straight line, and then we have vertically opposite angles. I'm being fast here. So what we know about a straight line is that this angle plus this one, so that means B1 plus B2 equal 180 degrees, and then reason angles on straight line. And with this one, I'm not going to talk about it. We know that 1 equal 4 vertically opposite angles, and we know that 2 equal 3 vertically opposite angles. And we know if we add all those angles, they must give us 360 degrees. That means 1 plus 2 plus 3 plus 4 equal 360 degrees, and reason will be revolution. So this was just me tapping on your prior knowledge, tools that you will need to combat this concept of Euclidean geometry. So now let's get right to it, to real stuff. Circles, nice, beautiful concept. So let's talk about the first circle. Okay, I will take this one. So this is O, that's A, that's B, and then that's C. So now, what do you know about this one, or what you have to know? This is what you have to know. I'll put a star and put a point. You need to know congruence. Yes, congruence, concept that you've been learning since from grade 8. So now, where do you use congruence? What does congruence mean? Because from my definition, it says same shape and same size. So now, we only have lines here. What is same shape and same size? So now, and do you know that the congruence, you used it mostly in triangles. So now, and we don't have triangles here, but you can create the triangles. So how are you going to create triangles here? By joining A to O, you see you have the first triangle, and then by joining O to C, you have your second triangle. So now that basically means to prove this theorem is not difficult. It's not difficult because what you know is you have to prove congruence. So now if you look at this thing, there's something that I should have spoke about on isosceles triangle. On circles, how do you see isosceles triangle on circles? If this is O, this is A, that's B. What can you say about OA and OB? Do they have the different length? Let me join. Do they have the different length? Never. You can measure them. You can measure them. If O is the center, OA equal OB. So OA equal OB. What will be your reason? Equal radii. And if you have this type of a triangle, what must come to your mind? The isosceles triangle. You need to know that the base angles are equal. So, but I will show you when we do problems how to highlight these things. So we're on congruence. Can you see that with that point? OA and OC. Highlight them from the start. OA and OC, they are equal. Reason equal radii. So normally they give you 90 there. So OA equal OC, reason equal radii. Remember, you to prove congruence, you need three conditions. So let's talk. Let's just say those conditions. Condition number one: OA equal OC. So OA equal OC. Remember, you need introduction. So we'll say in triangle ABO and triangle OBC. No problem. So what do we notice? OA, which is this line, and it's in triangle, in this triangle, is equals to OC, which is in that triangle. So we have one condition. Number two, what do you notice about OB? You find OB in triangle 1 and you find it in triangle B. So we can just say OB is common. OB is common. And then third condition, what you can say is if this one is 90, let me highlight, if that one is 90, what will be the one next door? It will also be 90. Why? Angles on the straight line. Therefore, we can just say O, B, A with a cap equal O, B, C with a cap. And then reason, they are both equal to 180. They are both equal to 90 degrees. Or someone can find that one first using angles on a straight line, no problem. So now this is the first theorem that you need to master. But once you see this, what must come to mind is that that angle is 90. And if that angle is 90, that means AB equal BC. So in summary version, because remember I said I'm not going to prove these things. So in summary version, what you have to know is if you have something like this, what you have to know is, let's say B1 and B2. Look at the line. The line is drawn from where? From center. And then go down and cut the chord which is BAAC. So now using this theorem, we can use it by saying B1 equal 90 degrees. Reason, line, which line? This one is drawn from center perpendicular to the chord, or you can say line drawn from sector bisect the chord. So the second one, as I said, I'll be fast on these ones. I'm not going to prove them. I'm going to draw three different shapes. So this is O, okay, this is A, this is B, and that's C, that's O, 1 and 2. So now three different shapes. So that's A, B, C, O, 1, 2, and then the third one will be O, A, B, C. So three different shapes. This theorem says angle at center equal twice angle at circumference. So I have three shapes, 1, 2, 3, and they are the same. This is the same shape. If you move them in your head, you'll see that you'll get the same shape. So now let's look at this one. They are saying angle at center. Which angle is at center? It's O1 and O2, but we're talking about one. Which one? Not the one that is inside. We're talking about the one that is outside. So O1 equal, this is it is angle. O1 equal twice angle at circumference being B. So that means O1 equal 2B with caps. And then what about this one? The one, if you take this B and put it on top to get this image, to get this one, if you take B and put it on top, are you aware that O1 and O2, they are going to flip? So if they flip, so 2 will be the one which is here, and then B will be the one that is on top. So we can say O2 equal 2 times B. What will be the reason? Angle at center equal twice angle at circumference. So with the third one, if you move C and put it here, let's say you put C there, are you aware that you will have the same image? You will have the same image. So that means this one, so that means here O1 will be twice C2. The same reason angle at center equal twice angle at circumference. So these two theorems, if you flip them, if you move them around, they will give you this theorem. So like this one, if you take B and put it on top, you're going to flip the 2 and 1. If you take B that side, the 2 will be below. So that means 2 will be here and then B will be there. Even with this one, if you take C and move it here, you'll see you'll get the same picture. So that means O1 will be 2 times C2. Theorems that you need to know. So welcome back. So we we are moving. As I said, we'll be moving at the speed of light because there will be a day whereby I'll be proving these things. But for now, I just want to show you what you need to know so that you can be able to combat questions, combat problems on Euclidean geometry and get maximum marks on this concept. So another one will be this one. You need to be good with reasons. Okay. So we have this one. So suppose this is A, this is B, this is C, and this is D. So now with this one, this is a cyclic quad. Why am I saying it's a cyclic quad? Because let's look at the points. Point A, where do you find it? It's on the circumference. Point B, where do you find it? It's on the circumference. Point D, where do you find it? On the circumference. Point C, where do you find it? On the circumference. So that means this is a cyclic quad. Why are we saying it's a cyclic quad? Because all 4 points they're on the circumference. So now, suppose you want to find angles which is equal to A. Okay, let me highlight this A. Suppose you want to find an angle that is equal to that angle. You can use these two kits, the pens. You can use your pen and a pencil. So the starting point, let's look at this thing. The starting point of these pens is going to be at A. And then where they stop, they must stop at the circumference. And where they go in a different direction, they must also stop at the circumference. So let me show you practically. This is basically a nice thing on how to find angles which are equal to A. So this is where you start. Okay, let me do this. So this is where we start. So what is the direction for this pen, or the direction that these pens can take? They can go down there, stop. Why are we stopping here? Because remember we said they can stop, or they must stop at the circumference. So this is where they stop. Do we have a different direction? Yes, we have it. So we go towards C, and this is where we will stop. So where you stop is the angle that is equal to the angle where you started. So we started at A, we use our pens, they will use our pens, stop, and then go to a different direction, and then we stop at C. So that basically means angle A equal angle C. Let's do the same thing, but moving from B. Remember, if you want to find an angle that is equal to B, use your pens. So here is our pens. This is a starting position. Are we at the circumference? Yes. So we are good to go. So now let's go. The direction, we move on the lines according to the lines. Stop. Why are we stopping? Because we are at the circumference. Do we have a different direction? Yes. So this will be our direction. This is where we stop. So now this is where we stop. Where did we start? We started at B, and then where did we end? We ended at D. So that basically means we can say angle A equal angle C and angle B equal angle D. What will be the reason? Angles in the same segment. So you need to know even the reasoning. You need to be good with reasoning. So angle A is equals to angle C, and angle B is equals to angle D. Reason being angles in the same segment. So now this one, let's look at it. The theorem says equal chords subtend equal angles. Equal chords subtend equal angles. The reason I'm putting it next to it, because if you can join B and D, if you join this thing, are you aware that we have equal chords for, let me hide this one, for this part, we have the same chord which is BD, and if I hide the second part, if I hide that part, we still have the same chord for that triangle. So now, since this is the same chord, A must be equal to C. So if you don't want to say angles in the same segment, you can say that angle subtended by same chord. So equal chord, subtend, equal angles. So now, if you look at this chord, let's call it chord 1 and then chord 2. Let's put some number in there. So now, if you look at this thing, chord 1, subtend which angles? You just go to straight opposite to angle opposite to this side. So which angle is opposite to this side? It's A. So that means angle A, let me put it here. Angle A is equals to, now let's go to the second chord. So this chord subtend which angle? You just go opposite to the angle, to the side. So the angle is D. So angle A equal angle D. So what will be the reason? Equal chords subtend equal angles. So now we know this one. I forgot what they call it. They call it butterfly. The butterfly type, it goes with angles in the same segment. So now moving on to the cyclic quad. So this is the cyclic quad. Remember, what did we say about the cyclic quad? All points, they must be on the circumference. So if you look at point A, point B, let's highlight them: A, B, C, D. All of them, they are on the side, they are on the cyclic quad. So now, if they are on the cyclic quad, what we know is the one that is outside is equal to the one that is inside, but they must be vertically opposite. So now, which one is outside here? It's C1. Which one is inside and vertically opposite to that C1? Is it this one? No, 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 no. Is it that one? No, 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 no. Vertically opposite, vertically opposite. So that means C1. So that will mean that, let me put it here. So that means C1 equal A. The one that is outside equal the one that is inside, but they must be vertically opposite angles. So that means what will be our reason? What is C1? Using the triangle. Remember the triangle of exterior and what we did in the previous lesson. So now C1 is exterior angle. So we can just say exterior angle of. But what is this thing? Is it a triangle? No, it's a cyclic quad. So exterior angle of a cyclic quad will be our reason. So you need to know this thing. So let's look at this one. This one, we know it. A equal D and then B equal C. And guys, this is not the same thing as, you see these two different things. Two different things. Remember, for us to say A equal D, all the points, they must be on the circumference. So you see here, the points that are not on the circumference. So if you see this shape, you must remember angle at center. Only if we have a center. So now let's look at this one. This one is, this is angles in same segment. And then let's look at this one here. This one, we are saying the one that are opposite, they add up to 180 degrees. But if we have a cyclic quad, if this is a cyclic quad, then the ones that are opposite, they add up to 180 degrees. So which two angles are opposite here? That's A and then that's C. So that means A plus C, they must give us 180 degrees. And the reasoning for the cyclic quads, the easy. So now A and C, what are they? They are opposite angles. Yes, they are opposite angles, but opposite angles of what? Of cyclic quad. And then you take the back. So now what do you know about B and D? Since A, B, C, D is a cyclic quad, therefore B and D, when we add them, we must get 180 degrees. What will be the reason? Opposite angles of a cyclic quad. Nice. So now moving on to the conjecture. So how do you prove a cyclic quad? And you have the answer. How do you prove a cyclic quad? What do you know about a cyclic quad? I know that the opposite angles, when I add them, they must give me 180 degrees. So if a question say prove that ABCD is a cyclic quad, the first thing that you do, identify on the side angles which are opposite and find the size of each angle and prove that when you add them you get 180. That's number one of proving a cyclic quad. Number two, find these angles. I'm going to show you. You find these angles, you write them on the side. And then if you can prove that those two angles are equal, then the figure becomes cyclic. So number one, find opposite angles, add them, find their size and add them to see if they give you 180. If they give you 180, the figure is cyclic. Number two, find these angles which are in the same segment. And if they are equal, then the figure, you can make a conclusion by saying, therefore, the figure is cyclic quad. Number three, A, B, C, D, 1, 2. So number three, if the question say prove that ABCD is a cyclic quad, you can find the exterior angle. Let's say the exterior angle, you find it and you get it to be 40. And then you find the interior that is opposite, you find it to be 40. So now if C1 is 40 and A is 40, what will be your conclusion? The conclusion will be A, B, C, D is cyclic quad. Why? Because exterior angle equal to opposite interior angle. So how do you prove a cyclic quad? First one, find the opposite angles, add them and see if they give 180. Number two, find angles in the same segment, see if they are equal. Number three, find exterior angles and see if they are equal. Basic things. So now, moving on to another point, which is a tangent. So that's A, B, C. Okay, we have our O there. Let's say this is 1, 2, 3. Let's say C. Okay, D, E. For you to be able to master this theorem, you need to know this statement. Angle between tangent and chord is equal to angle in alternate segment. Believe me, if you can master the theory here, what this thing says, you'll use your pens like we did with angles in the same segment. So now we have to check. The statement say angle between the tangent. So the tangent will be in blue. The tangent will be in blue. So they're saying angle between the tangent and the chord. So the chord will be in red, in bold red. I'll just do this. That's the chord. The first chord and then the second chord. So what does the theorem say? It said the angle between the tangent and the chord. Identify an angle that is between the tangent and the chord. This is the tangent. This is our tan, and then that's our chord. So if you look at this case on this side, Which angle is between the tangent and the chord? Thank you very much. The angle between the tangent and the chord is B3. So now you are going to place your pens, these two pens, on that chord you are talking about, such that the angle behind that chord is that angle that is between the tangent and the chord. So this is our pens. This is where you'll put it, and this is where you'll put it. So now if you look at these two pens, they are on a chord. So what is the angle that is behind that chord? Is B3. So we can say B3 equal. So now we move. So what is the direction of the pens? The direction of the pens, they are moving towards E. So that means B3 is equals to angle E. What will be your reason? The reason will be tan chord theorem. You'll see me using this depends more in activities that we'll be doing. So now let's move to the second chord. Remember I said depends, they must form a chord. So it will be from B to E. That's our second chord. So now what is the angle after or behind the chord? That's B1. So now you say B1 equal. Now what is the movement? Where are they moving? These pens, they are moving towards B. And remember the pens, they stop at the circumference only. They stop at the circumference only. So the movement of the pens, there they are. The angle that is behind, it's B1. So moving, and then stop. So that means B1 is equals to D. So what will be the reason? Tan chord theorem. So another thing on tangent, what you have to know, you need to know it because you're going to use it in circle geometry. Those who are in grade 12, I'm sure you can attest that you use this theorem a lot in circle geometry. So what we know is whenever we have a tangent and a radius working together, if those two work together, we get what we call orthogonality. We get orthogonality. It's a concept. It's basically a word for perpendicular. I'm sorry for being abstract. Perpendicular. So whenever radius, what is this thing? That's our radius. And then what's that thing? That's our tangent. So whenever the two work together, they form orthogonality, or they form perpendicular or something like that. So now we allowed to say OBC, since these two they form orthogonality or they are perpendicular, we can say OBC. We're talking about this angle. We are saying is equals to 90 degrees. What is our reason? Tan perpendicular to radius. Nice. So remember the pens, they help you to spot the tan chord theorem. And then remember when we have radius and tangent, we have orthogonality and perpendicular or perpendicular. So if OB is perpendicular to AC or ABC, that means OBC is 90 degrees. The reason will be tan perpendicular to tangent. So coming to a basic one, basic theorem of having two things there. Those who are going in the field of applied mathematics, you'll want to know how this thing operates or how this thing works, because if you can look at it, it's something like a chain. You know, the chain is something like this, and then you have a smaller one there. So that's something like a chain. So those who are going to do applied maths, you'll see such questions whereby they are more practical and more nasty on this thing. So I'll put stars How do you prove it? Then I will just put congruence. Congruence. So to prove this one, you'll need congruence. So how will you prove congruence? You need two triangles. How will you form them? You will just draw a line. So with that line there, you'll have triangle 1 and triangle 2. Condition 1, OA will be the common side. Condition 2, OB equal OC equal rad. Condition 3, remember what we said. We said whenever we have R and T, what must come to mind? The 90 degrees. So if this is 90, this is R, and then that's T for tangent, that 90. So OBA equal OCA. That will be our third conditions, and then we can make conclusions by saying tangent AB equal tangent AC. I'm not proving today, as I said. So what we have to know about this theorem is that the tangents, which is AB, equal to tangent AC. And then what will be your reason? Will be tangent from same point. So if two tangents, they come from the same point, they are equal. They are said to be equal. So AC equal AB, reason will be tangents from the same point. So I'm starting to feel like this is becoming theoretical. I think maybe if we can go through some activities to see how do we kill this thing. Okay, let me add another one there. Okay, I don't know how I always forget this one because in class I prove them, and then learners just give me, say you forgot about this one, and then that's when I prove all these theorems. J alone, I can't remember some of them. So, but this one is also important. So now, for module length, O is center, or from what you know. If O is center, what is AC? AC is diameter. If O is our center, this is R, and then what will be that one? It will be D for diameter. So if that is our diameter, I want to change some things with this theorem. Whenever you have a diameter, remove the word diameter in your mind and put hypotenuse. You know, there was one of the days whereby, you know, math can make you go crazy. I wrote an article on this thing, that hypotenuse equal to diameter, and my reasoning there, they were on point, but nothing to say. So hypotenuse, when you see hypotenuse, you see the diameter. Let me show you. This is, if this is a right angle triangle, and then this is hypotenuse, which angle will be 90 degrees? Okay, you can pause the video and then take a wild guess and then play the video again. So the angle that will be 90 degrees is the one that is opposite to the hypotenuse. So which angle is hypotenuse? Is opposite to hypotenuse? It's angle B. So that means angle B will be 90 degrees. So now, since we are saying hypotenuse equal diameter, so if we see this thing, we think of it as hypotenuse. So now, which one will be 90 degrees? It will be B. Therefore, the theorem B equal 90 degrees. B equal 90 degrees. What is the reason? To get the reason, I don't overthink. What I'll do is I just hide this part. If you hide that part, what do you see? I think I see half of a circle. So this is half of a circle. So this angle that is 90 degrees, where do you find it? You find it in a semicircle or in a half of a circle. So now the reason here will be angle in a semicircle, or you can say angle in a half circle, or you can say angle in half circle. Three of them, they are correct. So the idea, diameter, hypotenuse, the same thing, and then locate that 90 degrees, and then p equal 90, then you give your reason, and then you are safe. So now we're going to go through, in case there are those that I forgot, you can just highlight me or update me on in the comment sections, and then I'll just go through them. But for now, I just want us to go through activities to see how do you apply these things. But before, I want to make a short summary on everything. So now the first one, I'll be referring to all this information when I'm solving. So the first one, let's ask ourselves questions. How do you prove two lines are parallel? So the first one, you identify those angles which are corresponding, or you identify, I'll just write ID for identify, or let me be more mathematical, let ID be identify. So how do you prove that two lines are parallel? First, you identify the corresponding angles. You identify corresponding angles and show they are equal. So here, you identify co-interior angles and show they are supplementary. And then here, you also identify the alternate angles and show that they are equal. That's how you prove parallel lines. I'm going to show you how to do that. Identifying is important. You will decide. You either go with corresponding, either co-interior, or alternate. It's up to you. Point number 2. How do you prove cyclic quad? With cyclic quad, I was brief, or I went into detail, like you need to prove that remember what I said with cyclic quad, it's only on these three things. Cyclic quad, you need to prove that these two are equal. You identify them and then you prove that they're equal. So ID is very, very important in Euclidean geometry. Identify and show they are equal. Don't worry, I'll show you the application. But first, identifying the parallel lines, the corresponding co-interior and alternate cyclic quad, identifying angles in the same segment, identifying opposite angles that you are going to prove that they add up to 180, or identifying exterior being equal to interior. I will show you the application, don't worry. So now, the tangent, okay, let me before, how do you prove sides are equal? So now, to prove that two sides are equal, we use two concepts or two ideas. Now, the first idea is we use congruence. So if you can prove that two triangles are congruent, and then that will mean their sides have to be equal. Then the second one, we use isosceles triangle. We use the two to prove that two sides are equal in Euclidean geometry. but I will show you how do you go about with using these ideas. Geometry, it's all about identifying. If you can identify, then you can prove. If they say prove that a certain line is a tangent to a certain line, you need to find this angle and find that one. If they are equal, then this line is a tangent to that circle. So don't worry, relax. We'll be going through examples. I think in the next video we'll be going through activities. I have plenty of activities that I want us to go through. Just remain calm, relax. We're going to kill this thing. And please hit the subscribe button, share the video. Thank you.